In this lecture, we'll talk about vortex lines, sheets, and vortex tubes. Um, to better understand this, what we will do is let's go ahead and review what was vorticity. Just for completeness here, let's define again what was vorticity. And as we spoke before, vorticity is given by omega, is a vector, and is the cross product of the gradient times the velocity. Okay, and we define this as 2 times the average angular velocity of the fluid. Okay, and another thing we can also define this is the sum of rotation rates of 2 perpendicular fluid lines. Okay, by this what I mean is what you could have is a case like this, where you have a flow going in this direction, a flow going in this direction, and you can see that that's going to create a vorticity. You could have also, or you could also have a case like this, in which this is coming in this direction, but this is, you have a smaller vector coming in this direction. You have another vector coming in this direction, it's bigger, so the rotation now is going counterclockwise. Okay, so that is also true, and we defined then the rotation omega 1/2 the vorticity, and one of the things that we said about vorticity is if there is no rigid body rotation, there will be no vorticity. So if I say no rigid body rotation, then you have no vorticity. Okay. And another thing just to highlight here, the divergence of vorticity is always going to be 0. It's always going to be 0. Okay, and the vorticity is convective with fluid. Okay, so these are things that we already defined last time. Now, this time, I want to talk and I want to introduce what are vortex lines. When I talk about a vortex line, I am talking about lines of vorticity. So think if you have a line, there's a vorticity along that line. This is a vortex line. Okay, so you can think about a line that has the vortex line. This line doesn't have to be like this. The line could also be diagonal line. Is a vorticity. Okay, so it's a vortex line. So what is true about a vortex line is a line everywhere tangent to the vorticity vector. And then one thing is important, the vortex lines will never intersect each other, will never cross. And vortex lines are rarely streamlines. Okay, so another topic here that we use a lot is what we call a um, vortex sheet. Okay, a vortex sheet again. Think about a sheet, right? And somehow this is a plane, right? I'm taking a portion of this plane in space. So really it is a sheet in space. That's what I'm doing. And you got lines, okay? These are what we call vortex lines, okay? And they're all rotating, okay? So it's a sheet, and this sheet has vortex lines. And this concept is very, very important, especially when we will talk about several theories for lifting line theories and how you derive the lift. This concept becomes very important, okay? So this is nothing else than, as a formal definition, is a surface formed by all the vortex lines passing through the same curved space. Another thing that's important is there is no flow of vorticity through a vortex sheet. In other words, if I take the dot product of my vorticity by the normal times my area, that will give me 0. Okay, so if I have this, again, right, and then in this surface, I got this line, right, vorticity, this is going like this, I got a omega, and then you do have here a vector that's perpendicular to this small, maybe surface area ds, okay? This is the unit vector normal to that. Many times, basically, this is nothing else than, we do this a lot, and you will see that people write this a lot, is the dot product of the unit area. The area vector is nothing else than the norm of the vector times the area that you have there. Okay, so Another concept that we want to discuss here is called the vortex tube. So a vortex tube, think the same concept if it was kind of like a streamline. However, this is a vortex. So has so now you have all these lines that go here across this, right? But then what you have to think is these are actually vortex lines, okay? And all these vortices actually form a tube. That's what you really have. You're having here. Um, so a vortex sheet closed let's redefine it like this, a closed vortex sheet forming a tube, okay? So that's a vortex tube. Let me give you a couple of examples where you actually see these applications and why this is so important in the stuff that we do, okay? Let me give you this particular example. So you may want to pause and take this picture. Basically, what's happening here is, in this particular example, you can see that yeah, I have a circular cylinder. Let's suppose that this is rigid. We got a flat wall right here, and then you have a flow coming in this direction. And you have a boundary layer, as you can see here, that's being formed. Okay, you got this boundary layer. You have all this boundary layer that's actually being formed all the way through. And this boundary layer is actually cutting through, just think about if you're actually cutting through this, it is going to cut through the cylinder and it's going to continue. Okay, so that's the boundary layer. Okay, so let's see what happens if I look this boundary layer from this side here. So if I did that, you bounded a side view of the same thing will look something like this, right? We talked about what was the boundary layer. This is the flat plate, and then you have the circular cylinder. Remember, the circular cylinder just went all the way through. So this is what it looks like. Now what we're gonna do is let's make an imaginary cut somewhere there and look what happens from the top. So if I'm looking from the top, what's happening is there are vortices, so you can see these are what we call streamlines, right? These are streamlines. And then my fluid is flowing. Because my fluid is flowing, just know that what's happening here really is because of this flat wall here, my fluid wants to have a temptation to try to, it's going to try to do this. It's going to try to rotate, right? So it's moving here, and think that I got a bunch of lines that want to actually rotate about this, okay? They want to have some rotation. So the whole fluid here, what they wants to do is it wants to try to have a rotation, okay? So those are what we call vortex lines. Those vorticities, small vorticity, each particle is trying to rotate, and as it's getting closer to this, what's happening is now your fluid is separating, right? But it still wants to rotate because of this flat wall. So therefore, this is what your vortex lines actually look like. Okay, so these are some of concepts that are very, very important as we move forward, and they're going to work. They're going to serve the foundation for all this circulation and the vorticity concept that we're going to learn in a few minutes, in the next lecture.